Well, let me start by congratulating SPEEDUP and thanking you for giving me the opportunity to talk about where we are today in Switzerland. And I know a lot of colleagues in the SPEEDUP community, and I know the importance that you guys play in scientific computing in Switzerland, and I hope some of this will also be clear from my presentation. Is this okay? You hear me not too loud also? Okay, so let me start with basically saying where we are now. You can only look into the future if you know where you start from. And there may be some confusion as to where we are. When I came in 2008, actually I came to CSCS but because I realized CSCS had actually a very, very strong team of people. And trust me, I would not be there. I would never have moved if I hadn't seen that. That there's a huge opportunity. CSCS had also started one of the first in Europe to go into this massively parallel era. Now nobody questions it. But at the time, I know people, my current colleagues at CSCS took a lot of criticism for doing this. But it's basically this foundation that we could build on. And also one thing I would like to acknowledge, because you were acknowledging Helmar, people, I think there's two people that stay in the background here, and that's Ralph Eichler, the president of ETH, and Piero Martinoli, the president of University of Lugano, who have been really pushing this initiative, plus a number of other people behind, at the ETH level, ETH board level, and so things were really aligned, and so things happened very quickly. And so what we basically started off with is the realization that in order to prepare applications for anything, you have to have a machine that looks like a machine at scale. And that's why Monte Rosa was introduced in 2009. The other thing, and it was then upgraded, the next thing we did, and that's really, it was an idea that basically came out of, I guess, some frustration I had when I was at Oak Ridge National Laboratory, and Jack, I guess, can understand why. It was basically we need to invest in applications, and so we had a part in the budget of this high-performance computing and network initiative, the networking part, that was not very defined where it should go, whether it should go into grid computing or into buying clusters, and we proposed to build a human network, and we created this high-performance computing, high productivity and high-performance computing initiative. And so this was this investment that you've heard some talks. I will come back to this. We had the final upgrade of the KXD5 to KXD6, and we are planning now to invest in new machines. But in order to have new machines, be able to run new machines, we had to build a building. And this was just inaugurated last week. But we moved in March, April. This was a very challenging time, as you can imagine, to move all this equipment into a new building that is very sophisticated. But I think now we've really did this. Note the amount of time it took to build this, and to basically pull a water line across the city of Lugano. I often get asked, whether Standort TC, whether this is a problem or not, and I don't think we could have done this in Zurich. I'm saying this, maybe it's politically incorrect, but I really can tell you this was done extremely swiftly. This is the high-performance computing and productivity high-performance and high-productivity computing platform, HPC, is basically an investment into application projects, and the idea was to fund, rather than fund people at the center who help applications, to directly fund HPC competence in application teams. And for some, I think, strange coincidence, the first two projects on this list were also the two projects that you heard of today, Laurent Villars and Jörg Hutter, but Joost van der Wondele gave the talk, but Jörg Hutter is the PI. And it's basically, you can pull up similar stories from each of these projects. This is just the background of HPC. Now, as we move into Exascale, and this is what I have to talk about, I think it's, I will quickly give you my perspective of what I think Exascale is. Obviously, we talk about the same metric, flocks. Jack and probably large parts of the community look at moving to Exascale with an impact benchmark. I like to think in terms of sustained application performance, and this story of sustained application performance and impact seems to be very coherent over a long period of time. We had the first petaflop in '88, the first teraflop in '98, and then the first petaflop in 2008. So I think a bit faster than what you see on the impact side. I firmly believe that the case is there to have an exaflop towards the end of the decade, and I made the statement that I think you will see this in applications, maybe even before you see it in impact. But that's, we're all young enough that we can check this in a few years. We also heard about this, and we heard about the concurrency. We heard about power, and since I'm a director of the center, you can believe me, this is one of the things that interests me more than I ever did before, because it translates directly into millions in my budget, of also order of millions, so it's a substantial fraction of the budget. But there's another point I want to focus on. So you can focus on this, and you can say, machines are going to be built and so on. But what I think what is really needed is you need two things to develop Exascale. First, you need a need to have that. And I'm not going to spend much time on the science case, but I could spend a lot of time on individual science projects and articulate the need. So if you have the need, and you have somebody who develops the technology, Exascale machines will be built. And I want to point to this observation. These were all custom-built high-end processors. This machine, and it basically stands for a set of machines of that era, and that we have since, was built on commodity processor, unlike the previous ones. And at the same time, in the same year, the machine that gave rise to the first sustained petaflop on Limpac, namely Roadrunner, was built on cell processors and Octeron. So this is a trend that you see more and more. Currently, the top machine and last year's top machines are not. So Blue Gene and K-Computer are custom-built processors. But I claim that this is going to stay around. And why? Because of these numbers. I received this from Andy Keane, so this is the first time. It takes $500 million, roughly, to develop a processor. If you know what you're doing. If you don't know what you're doing, it takes a lot more. If you have $500 million to give to a company, they will create a processor to your design. And it turns out for the K-Computer, that's roughly what they did. And the K-Computer has a budget of 1.2 billion, about $500 million of that is the development of the Spark process. Most other projects don't seem to have the same amount of cash as the Japanese projects. If you want the company to develop a processor, they need a revenue, say, of over 2 billion to justify this investment. That's what Andy Keane, when at NVIDIA, was saying. And then he made a calculation. If they were to fund this just based on parts they sell to the HPC market, a processor would cost $13,000. Now, exactly how we got there, there's probably a lot of NDA information we're not supposed to know. But I'm sure for any other company, roughly, it would cost an order of magnitude more than what we are used to pay for a processor. Okay, so we need this market, and the point is that the movie gaming market is a market that has enough affinity with what we are doing in scientific computing that I believe this is the market that will fund the development, whether it's at NVIDIA or at Intel or whatever other company. I don't know which company we will buy processors from in 2018, but we have the market that funds it, we have the science base, and that's why I believe it will happen. I want, in my talk, to motivate what we do in Switzerland to give an application perspective. So we had 2 application perspectives also already. I will add 2 more, and I will put my emphasis even more than in the previous one on this issue of algorithms, and not for the sake of just algorithms related to methods, but algorithms related to mapping onto a machine and also the software development. And I want to do this with something from material science and something from climate. And then discuss how we take the strategy forward. There are no big changes to the strategy, but some adaptation that we need to see. We've heard about the prevailing equation, called charm equations, in Jost's talk. The typical ansatz, which is in some basis set, you develop, expand the solutions. And this leads to a Hermitian Hamiltonian matrix and an overlap matrix and a generalized eigenvalue problem, Hermitian eigenvalue problem that we have to solve. Now, you trust me, I had somebody ask me today, why are there so many material science codes? Because there are probably 50 different ways how you can approach solving this problem for real materials. And what I'm now trying to do is try to categorize these methods. And one that we heard about this morning, I'm not going to talk about, not going to repeat, but I truly acknowledge, of course, that it exists and it's a very potent approach. But the first type of methods, and for the experts, is something like LAPW, or so is optimized, the basis set. And the basis set may then be very awkward mathematically to deal with. That's why many people don't like it, but the point is they are very efficient because you will end up with a matrix that is, I'd say here, 2 to 10 times larger than the number of electrons that you have to solve, and you really have to solve this. This is your general, your dominant motive. The second class of methods, and the important point is, we need the eigenvectors to construct the densities that go into the potential. So it's fundamentally just knowing that spectrum is not enough. We need between 20 and 10 and 50% of the eigenvectors. The second class of methods is you approximate this potential to make it nice so that you can use analytic basis sets like plane waves, and then you end up with a matrix that if you could never store, so you have to use iterative schemes to solve the eigenvalue problem, and you have to go, when you use plane waves here, you go from a reciprocal space representation for parts of the operator to real space representation, so you have Fourier transforms that you introduce, and you end up using still an eigenvalue problem, but here more like a preconditional, kind of. And so you end up with motifs like FFT orthogonalization or generalized eigenvalue problem. What Paul Kent was in my group in Oak Ridge already in 2008, but the work was done in 2007 with a well-known code VASP, showed that the scaling of all these other things is not the problem. The problem is really always with the linear algebra part, so the eigensolver part, that you need to either figure out how to scale or how to bring the time to solution down, that you just don't care about this. Okay. How large is n in these matrices? So as a mathematician or high-performance computing guy with a large parallel machine, I like to make n as large as possible, because then you can show how things scale. Well, n for there's a theorem by the same author of density functional theory, Walter Cohn, that argues that in a high accuracy quantum simulation you never have to go to more than, he may even say less than 1,000 atoms, but don't have to go to much more than 1,000 atoms. That has to do with physical properties of the electron fluid. So an all-electron method, where you treat all electrons explicitly, you will never go much more than 10, 50,000 electrons, and that will lead to, to matrices that are maybe of order 100,000 at most. The pseudopotential methods, n, can be as high as a few thousand. So the matrix is either 100,000, that's really the upper limit, but typically it's more of order 10,000. If it's 1,000 or less, you don't have to worry about it. But if it's of this order 10,000, you have to worry about it, but there's no easy way to kill the problem with scaling. Okay, so this basically gives the range of the problem. Now there are cases, and so I don't want to invalidate what Joost said this morning, when you want to, instead of simulating structure or properties of a material, you want to simulate a device. And you have to do a quantum transport simulation through a nanoscale device. Then your n might be much larger. But then you can compromise typically on accuracy. And then you don't want to use these n-cube methods, then you want to go to this order n method. That gives you roughly the picture. This is just a result of what are I would say, the most used library today, ScaleAttack, and probably the highest performing library today at scale is this ELPA library, this development in Germany. Now this paper is a little bit dishonest. When you look here, the difference between ScaleAttack and ELPA is roughly a factor of 4. This is a result. They show for real eigenvalue problem there is no real quantum mechanics. You have to do a complex matrix, and there the arithmetic density is a factor 2 higher, so it's really the factor 2, the difference between ScaleAttack and ELPA. But what it shows you is the scaling, particularly on Intel-based machine, is pretty good. Scaling, and particularly the time to solution, is very good on this library. So I will talk a little bit about the algorithms behind this, and the next step is also some other considerations about implement. So this is the problem we solve, and I don't think in here I have to say much. That the first step is to transform the general eigenvalue problem into a standard eigenvalue problem, and then go about solving this. The traditional way is just by tridiagonalizing the matrix, solving a tridiagonal eigenvalue problem, back transforming the eigenvectors once and then a second time, and then we have the eigenvectors to go to take the construct the charge density. Turns out this is what we call the one-stage solver, and it's dominated by Blas level 2 operations in this tridiagonalization part. And this is on a modern processor. I guess you know more about when you started writing way back, but today is probably not the most efficient map onto the architecture. And so that's why ELPA, but also our collaborators in Knoxville, have been looking at this more complicated two-stage solver, where you go from, instead of going directly to a tridiagonal matrix, you do a reduction to band and then a tridiagonalization of a banded matrix. And the price you pay is you have to do one more back transformation. But it turns out those are things you can easily parallelize, and that's why ELPA ends up scaling so well, because the part that doesn't scale well is basically shrunk, and the price you pay you can do well at scaling. And the interesting thing in this is, and this is not a new idea, this has been around for a long time, but it's basically you go from previously Blas level 2 operations, you you go to these class level 3 operations, so you have increased data locality in your algorithm, and that you'll map now better to the architectures. Now the interesting thing is that you can also have a hybrid implementation of this, and so the idea is to do this QR decomposition, now panel by panel, and the nice thing is that you can, so you have the decomposition of one panel, you have the update of the rest of the panel, the matrix, and the good thing is you can overlap the new panel you're working on with the update of the rest of the matrix of the previous panel you have worked on, and you can do this on a hybrid architecture, parts on the CPU and then parts on the GPU, and so you end up really with a truly hybrid implementation of this reduction to band part. These two parts are done on the CPU, and then the expensive back transformation is more class level 3 operations that you do on the GPU. And then you see what happened basically when you compare now the 1 stage to the 2 stage, and this is on hybrid, but on multi-core looks the same. You've basically shrunk away the tri-diagonalization part. You've introduced this penalty, but if you're only interested, and this is in part of the eigenvectors, which is the important part for material science, you don't have to back transform as many eigenvectors, and so that's where you end up gaining. And this is the comparison now MKL and LK to this hybrid implementation. So we have basically two wings here. One is the wing going from the 1 stage, these two to these two, or these two to these two here. And we have the wing going from taking one of the processors out and replacing it by a CPU. So you go from this point here, time to solution, over a factor of 3 to this point here. So new algorithm and hybrid implementation. And this is significant for these wide range of applications. The second one I'm discussing is these climate codes. I don't want to give a big background on climate. I'm not a climate scientist, so I'm really getting out in the woods here. But I've been working since I took over CSCS. Of course, we're very interested in this problem of weather meteorology in Switzerland, because CSCS is running the systems that run the simulations for Meteo Suisse. So the weather forecasts you see are based on these simulations. We have no way of influencing the weather, although right now it's good outside, so everybody's probably happy anyway. But the way these things work is we have global data and simulations coming in from this European Center for Mid-Range Weather Forecasting in Reading, and so this is basically the initial and the boundary conditions that go into a 7-kilometer resolution model over Europe that create the boundary conditions and the initial conditions for a high resolution 2-kilometer resolution simulation over the Alpine region. And then this is used, done 8 times a day, and is used to produce the weather forecast. The code behind this Cosmo code is standard weather, so it's Navier-Stokes, or in this case Euler equations. So the abstraction at the point of this discussion is PDE on the structure tree. Physically, when you look at the mesh, it has this, I said 2-kilometer resolution is the highest lateral resolution. It has a much higher resolution vertically, and so this introduces the shortest time scale you have to integrate over. This code, they decided to do an implicit solve, basically split the problem in 2 parts, do an implicit solve here vertically so they can use larger time step and do an explicit solve for the rest.
Is it fully implicit or is it just semi-implicit?
It's implicit.
Fully implicit, not semi-implicit.
Well, you said semi.
It's semi-implicit, the whole thing. So the main point is about this is basically it introduces two motifs. One motif is the stencils that you one motif is the tridiagonal solve in the vertical direction, and the other one is the stencils that you have in structured grid codes. And the reason, so this is on, and there are other codes like WRF also that are explicit and don't do this thing. They run a little bit slower, but they are nicer to map onto a parallel machine. This really introduces a problem because you have two motifs that compete with each other. This motif prefers a column first storage. This motif prefers a plane first, or XY direction first. And so you can imagine, in principle, this is a very interesting optimization problem for computer science and so on. I don't have to say much to this audience that stencils are memory bound and that you have to look at the machine differently than when you solve an impact problem. So the question is, in terms of accelerating or speeding up this code, or making the code more efficient, you have basically two alternatives. One is to do some cleanup on the algorithms, but the other is really choose the hardware. And as I said before, the stencils are memory bandwidth bound, so this is where we have been looking at, for example, GPUs, not for the flops, but just because the fact is they have a higher memory bandwidth, and it looks like in the future that the scaling up of memory bandwidth there is probably going to be faster than on the general DDR memory. So this is really one thing we were looking at, but then of course you immediately see people say, but you cannot look at this because you cannot, you have to rewrite codes. And but one of the aims of this HP2C program is to solve, to attack this problem of rewriting codes. And so in particularly in the case of Cosmos, so this is a pie chart of this code being the fraction of the lines of codes that it's a Fortran code, about 20% is in this dynamics part, which amounts to about 60% of the runtime of the production problem. Another 20% is here, which represents 20%. So you easily see this is the problem you have to attack somehow. And after a long consideration with the community and what can be done about the performance, we decided here to rewrite this in C++, leave this in original code in Fortran and maybe optimize that in various ways. In order to hide architectural complexity, the obvious thing to do is develop a library. And since there were no generally commonly accepted stencil libraries, we had to look into developing a stencil library. One of the main goals was hide or abstract out the hardware platforms, but also hide a lot of optimization things that some of these climate codes can do hardly. But writing a library for this problem is not trivial because you don't have this one hotspot that you can work on. It's basically, these are the equations they solve, and you can see you can see these things as, there's more than like one or two differential operators you have to solve when you solve wave equation. It really is all computable. There's not a very high complexity here like in Schrödinger equation. But it looks intimidating. And so it really means writing a library for this problem is not straightforward. Because there's no one place you can work on. and there is, I say this, a countable but infinite number of interfaces that you have to have, because even in climate, there's no guarantee that it will be limited to this set of equations. You will probably expand the model, change the model, and so you need to keep the library flexible. So the idea was then to resort to something like a domain-specific language. Since we're in C++, it's embedded. And really the approach is to split the problem up in two things. When you look at one of these stencils, split the problem into loop logic and the actual operators that you have to update. And so that's basically this. You can deal with functors in C++, and this is what we introduced the domain-specific library for. And just very briefly, the whole thing is really, not just because of the numbers of stencils and so you have in this code, but also the way the level of approximation changes depending on where you are in the domain. And intuitively you can say, in their case, they have, take Switzerland and the atmosphere over Switzerland. You have the first 5,000 meters, you have a lot of corrugation, so you make coordinate transformation that introduce a lot of cosines and sines. And then you have the upper part of the atmosphere where you just can get rid of them. And so they in fact treat the two domains differently. And that pays off in speed. And if you cannot, with your new code and new library, do that as well, you will lose afterwards in your performance. So this is just a message to all the computer scientists, and I hope there are some that are thinking about stencil libraries, that we really need to discuss this at the level of real applications to develop something that is, really has impact. So the result is, in this, we did a first pass at developing this library. The library has two backends, one for CPUs or x86 with a storage order optimized. For CPUs there it's better to do this column first storage and use the cache for the tridiagonal solve, and then the other one for GPUs with the plane first. And this is just a relative performance thing. It shows again that we have many stencils. Understanding the performance of this code is not straightforward, but the final result is the rewrite led to an acceleration between a factor 2 and 3 just on the CPUs. And this is starting with a well-optimized code in the first place. This is usually where you see that when you hear reports about things running 50 times faster on a GPU, or even on mine, the first factor 20 is coming from just rewriting the code. Here it was harder to get a factor 20 because the original code was well optimized, but it shows it can still pay off. And then the GPU backend then has here an advantage because we have more memory bandwidth as expected. Okay, so the details of the numbers don't play a role. But now I want to summarize basically what we have seen in both cases, and implicitly have seen in the two projects you heard before. You start with the model, and the model is usually in the head of scientists. You then have a mathematical description, so I'm using the climate model, but you can put the chemical compound here, and you can put Schrödinger equation here. And then you go with the discretization and algorithms that we all know very well. Without this, we don't do anything on the computer. An implementation, a code, in this particular case a stencil, a human readable version, and then a compiled code onto a given architecture. And this is basically, I think, the way most of us agree this is how things are done in computational science. I deliberately put that this is a YMP. At the time when I was a graduate student here at Zurich, that's what I was using. And I think at that time, the world was still in order, because I think this is how things really were done and still work. At some point, we realized that things started to change, and we have to we start writing codes on a workstation, and then we think about vectorizing later. So we vectorize, and then we write the code, and then we parallelize it later. And that in the European projects we talk about petascaling, exascaling, and I think at that point you realize that something is wrong with this model, and why we need to take a different approach. And this is, I think, given that we had the HP2C program in place, and we had a lot of flexibility on what we do, we could basically decide to look at these things differently. And the situation is really the given computer, this one monolith that you work towards, has also gone. Okay? But rather what we have is architectural choices, particularly today, with even at the level of Intel, we are not just going to have Xeon, we will have Xeon 5, we have these GPUs, so we have these choices. And the point is that the interactions between these different parts are much more complex and interactive. I think most physicists know that, and probably, you know, it came certainly clear from Laurent's talk. There is, even here, there is an iteration between model and the mathematical description. That's where we usually lose our colleagues in the math department, because the physics is forcing us to go much faster than you can, sometimes even faster than you can apply rigor. But of course, we always have to stick with rigor, but it shows you we have these iterative realities also between models and algorithms. So the things that Matthias Troyer is doing. If your algorithms scale exponentially, the complexity, you're done. You have to inform the algorithm with the physics to really home into the parts. So we clearly know this, but what is now coming with this architectural diversity is that this is going to influence implementations and is also influencing algorithmic choices. Okay? And I hope the cases I've show you in reality this happens. Okay? We have architectural choices that drive us to these new implementation that lead also to acceleration and cost savings and everything. So this thing that software is expensive, at some point software is actually not more expensive than the power you burn in the end, or the power you save. I think I can show this in the case of the Metro Swiss application. But also this thing about algorithms are influenced by the architecture that you map on. Okay. So the question is now, how do you organize this? And what I claim is you really have to accept the drivers. And the drivers, as I said initially, you need science programs to drive exascale. And you need some market, somebody who funds the hardware. And so the natural drivers are, the science will drive this part. The vendors, because they make money in other places, that they are much, much more potent than the funding we have for science, will drive this part. And the tricky question is how to make sure that these two parts, the math, applied math, and the software investments, are not forgotten or chewed up somehow. And so I think HP2C was a first step that was, I think, quite successful in trying to really fund these parts and enable these guys to talk to each other. I think we've really reached this point. And this is what we now need to capitalize on and improve as we go forward. And so the HP2C project is coming to an end at the end of this year. But we have a successor or a new project that we call Platform for Advanced Scientific Computing, PASC. It will be funded as a structuring project by the Swiss University Conference. A final decision, as I have to say, I hope it will be funded, but I think the stars are still aligned. A final decision is expected in this fall, and it will be running in the next fiscal period in Switzerland, which is 13 to 16. And the lead is by University of Lugano with collaboration with CSCS, and I do expect that the current players will continue to play in some form, and maybe there are other universities that will join. The task will continue to be driven by domain science development of Swiss HPC. The specific aims is, and this is probably the one for most important bullets here of this whole talk, if you're interested about the strategy. We are starting off with a call that is already ongoing of trying to structure the domain, the science communities in HPC. So we have a call for that is actually using money from the HP2C program, because the new money will only be available next year. But the idea is really to get the computational science community to group around certain problems like in biology or material science or physics or engineering or geoscience, climate. We have an open call. I cannot select or say what they are before we have proposals and we have a transparent peer-reviewed selection process. But it is very important that this come first, because this is where the scientific drivers will come from. And our initiative in Switzerland will really build on scientific drivers. We are not saying we want Exascale. We are saying we want the problems that we are going to solve. And I'm pretty sure they will need Exascale, but we have to articulate those problems, and I want this to be done by these communities. And then these communities will be charged to develop an application support network, because I would like to decentralize this in Switzerland. I don't want CSCS alone to do application support. We have a lot of very great groups in Switzerland who develop applications, so they should be basically help drive the application support. So this should come out of these communities, and then these communities, based on the scientific goals they have, should then formulate co-design projects. And there will be a call coming out end of the year, early next year, for co-design projects, and that's really where the succession to HPC is going to happen. We also have some support for institutional cluster. This was mostly driven by needs from Cadmus, but there is also money for other universities. And if we continue to build what we have with HP2C, and I'm convinced we can continue to do this, then I think we're also in a position to use these communities, these co-design projects, to ultimately drive the design of the systems that we are building at CSS. And I think this is where things really have changed compared to what we heard in the 80s or 90s. Today, we don't go to a vendor and say, what is on the market, what can we buy? We are working in collaboration to build the systems we need for the scientific goals that we have. I think that's if there's any qualitative change, then this is it. So that's just now a summary of, we just inaugurated the new building. We are starting to build this over 3 years, this new supercomputing system. We start up with us. And this is the important point, that the ETH board now views supercomputing as a scientific research infrastructure, which means we are not funded on a project basis anymore, but we're really part of the funding cycle. And since our next funding cycle is 13 to 16, we already have to put in the plug that in 16 we start building the next system. So that's just for your information, that we are really looking at an infrastructure and not just a project machine by machine anymore. So the focus should not be on individual system. I just want to acknowledge, of course, the technical part particularly. There's people from Jack's group and a student at ETH. There's a great team, and this is just an example of a team. Laurent could probably put up a similar example, or CP2K or Petaquake. Each of these 12 projects can put up such a team, I'm sure. And the last one, I guess, for discussions. If you have questions, if not, I ask you a question.